Okay, so let me start while people keep on arriving. Welcome everyone to the ELLIS and UniRep speaker series, where we receive speakers that are of interest to the UniReps community and the topics that we are interested in, which the goal is to discover why, when, how distinct learning process yield similar representation and the degree of which these can be unified. Um, and today we have the pleasure to welcome two speakers. The first one is Yilun from Harvard University Kepner Institute. Today we'll talk about the generalizing outside of the training. The talk will be about generalizing outside the training distribution with compositional generative models. And then we will have a flash speaker, which is a 15-minute talk by Sihyun. And his talk will be about representation matters in training diffusion and transformer. Next, after these two talks, we will have a shared Q&A of 15 minutes. So if you have questions, make sure to write them in the chat, and we will, at the end of the talk, go back to them to ask both of our speakers. And if there are questions that are common to both, this is also really interesting. So yeah, welcome to our two speakers, and I will let Yilun start.
Uh, Great. Thanks for the introduction. And yeah, thanks everyone for coming. So today I'll talk a bit about some of the work we've been working on trying to essentially use like generative models and composing different generative models as some type of representation to allow you to generalize outside the data you've seen. So a lot of the goals of my research have been driven towards trying to construct more general purpose robots. And if we look at current robots, they are pretty simplistic in the tasks they can do. So here it's trying to pick up a couple of fruits, but if you slightly change the objects, you slightly change your goals, suddenly these systems start breaking. So I feel that like in contrast, if we look at humans or like all the intelligent robots we see in movies, they're able to solve all these tasks autonomously that they've never seen before, and be able to generalize to all types of new environments and other agents. So one question is, how do we build systems that can really generalize in a similar way to all these different situations? So this talk will be a general approach towards solving this, and then I'll talk about some key components and results. So the overall general approach is that we should really try to build some type of generative model that roughly represents the entire world. And then I'll talk about how once you have this type of generative model, now you can actually predict and plan adaptively to solve new tasks through a test time search. And then how you can really build these models in a compositional or modular way so that they can generalize to areas you don't have data in. So let me first talk about this first point. So let's consider a simple task. So here we have this image in front of us, and we have this task. We want to climb up the stairs. And my neural network can just predict this action trajectory of climbing up the stairs. So this is really great when the test task that you want to execute your neural network on is exactly the same as your train task. But in practice, a lot of times there's going to be these changes in the environment so that you enter these states that you don't expect. And the question is, how can we get systems that can really adapt to these new constraints at test time? Because in the physical world, we always are entering these situations that we haven't seen before. And the idea is we can learn, instead of learning explicitly what to do, we can instead learn a preference for every single action or learn some type of likelihood function. And essentially, this is what you do in a probabilistic generative model. So in a probabilistic generative model, you take an image as well as a trajectory, and you predict a likelihood, in this case, the energy. And then essentially, this model assigns the energy to every single possible trajectory that you could possibly execute. Where this energy roughly represents the negative utility of your action. So if the action is good, the energy is low. And if the action is bad, the energy is high. And now to really be able to determine what to do in this scenario, what you do is you simply just run inference on this model and try to find a trajectory that has minimal energy under their generative model. And the real benefit of this is the idea of a test time adaptation. So now if you have new constraints, such as I want to make sure that, that my robot is safe, or I want to preserve the battery life of the robot, or so forth, you can just define these new test times, new prediction time losses, or like costs is a separate energy function. And now you can just jointly try to optimize both of these energy functions at once and infer an action that minimizes the overall energy. And essentially, so this formulation of prediction using probabilistic generative models to make your decisions really allows you to use search to generalize to new settings. So that's the first idea. And the second idea is this idea that we really want to build these models or generative models in a way that's compositional so that you can generalize in areas you don't have data in. So we've all seen how powerful language models are. So if you ask language models how to build AI, they can give you these steps. But in contrast, when we try to use these same models in pretty simple multimodal tasks, so even if we just ask the model to understand the physics, for instance, if we say, where should I put an object so that we want to make this green ball into this blue, below and into this cup, now it becomes really complicated, or these models don't work very well because this is very different than the text information that the models have primarily been trained on. So in general, what we find is that when you apply current generative AI systems to things such as natural language, they perform pretty well. And we think that this might be because really the training data you've trained the language model on is roughly covers where you really want the language model to execute in the real world. But in contrast, when we consider things such as a physical robot or these like even these simple physical puzzles or images or so forth, it turns out that the training data that you see on the internet really is only a really small subset of what you really want your system to operate over. So we find this a lot in robotics where you simply take any of these off-the-shelf vision language models and you try it in actual robotic settings and they just don't perform at all. And it just seems like in practice, like the amount of data or the data that you have for training these systems in the embodied setting is just like isn't enough to allow them to really work well in all the real world settings. So the second idea I'll talk about is this idea that we can really use generative models, or in particular energy-based models, as a probabilistic way to actually represent real distributions and allow your systems to generalize it in a certain way that you don't even if you don't necessarily have data over it. And the idea is that like we want to decompose the world in the same sense that people have been building graphical models in the past into these individual factors. And then essentially we assume that our distribution can be represented as these independent subparts. Such that when we combine all those independent subparts together, we can represent the entire distribution of interest. And in this setting here, so I show that these factors are completely independent. In practice, they don't have to be completely independent. So you could imagine that, let's say you have like three variables, x, y, and z. You could have a factor over x, y. You could have another factor over y, z, another one over z, x. So roughly, these factors don't have to be fully independent. But if we assume that the world can be decomposed into this representation or these like individual generative components, now, since these components are independent, we can recombine them to allow our generative model to be able to actually generalize the new areas of the training distribution that you don't explicitly have data over. And of course, because we're making these assumptions are not fully accurate. It turns out that there isn't a perfect decomposition of the world. But you can imagine that once we have these like individual components, we can learn some type of residual model to actually learn the interdependencies between these factors. And it's really the interdependencies between factors that you really need online experience to cover. Okay, great. So that was just a brief high-level spiel about what I will talk about. So now let me talk a bit about some more the key components for this approach. So first, I'll talk a bit about energy-based models and energy optimization. Then I'll talk about how this type of compositionality allows us to do planning. And finally, I'll talk a bit about how it enables us to do reasoning. Okay, so let me again have an example of an energy function. So here, let's assume we have some type of energy function for red trucks. So we have this red truck energy function, and now when we get it an image of a green truck, it assigns it high energy. And in contrast, if we give it an image of a red truck, it assigns it low energy. And now this energy function roughly allows you to capture a probability distribution over the data, such that all images that are red trucks have low energy, and all other images have very high energy. And this energy function can be used to encode the log likelihood, or you can use this to encode the probability distribution you care about. And one way to think about what this energy function is that it's basically a verifier over the entire space of generations. And now once you have this energy function, how do you actually scalably sample from it from very high dimension in high dimensional spaces? So in like in late 2018, we proposed a really scalable way, which is to roughly just use the gradient of the energy function plus an added Gaussian noise. And roughly the sampling looks like this. So you have some starting initial kind of noisy image, and as you run the sampling, eventually you get a ground truth image from it. And to train these energy-based models, traditionally there's this type of maximum likelihood training objective where you draw some samples from your data, you decrease the energy of those samples, and then you draw some samples from your EBM or your energy function using the lens-driven sampling procedure I talked about earlier, and you increase the energy of those samples. And we essentially showed in early 2019 how like you can really train these energy-based or you can scale these energy-based models to pretty modern generative tasks. So energy-based models themselves are a very old class of generative models. I think most of the early generative models in deep learning were energy-based models. But we illustrated how by using a combination of this type of contrastive loss as well as this sampling procedure, we can scale these EBMs to more complex high-dimensional domains. And this is a rough intuition of how training works. So at the beginning, you have this somewhat flat energy landscape where everything's assigned the same energy. Now you have these negative samples, which is this Gaussian noise, as well as these ground truth images. And what you roughly do is you just pull up the energy of the Gaussian noise, decrease the energy of the real images. Now you get a more evolved landscape where now if you draw a sample from this more involved landscape, you get this, you again get this slightly the noisy red car, but now it looks a bit closer to the images you've seen before. And once you have these images, you again increase the energy of this noisy red truck while decreasing the energy of ground truth red trucks. And you repeat this procedure until the energy function has local minima exactly at images of red trucks. And at this point, you're decreasing the energy of red trucks while you're also increasing the energy of red trucks. So this means that you've converged to your final distribution and you've learned your energy-based model. And so you can actually, and this looks, so the lens-driven sampling procedure as well as the sampling procedure I talked about earlier looks very similar to diffusion models, and there's a pretty good connection between them. So this was the sampling procedure we proposed in late 2018. So you can see that from starting from Gaussian noise, as you run the lens-driven procedure, you essentially generate these images. And it turns out that with diffusion models, you can just interpret them as energy-based models. So roughly the denoising function in the diffusion model is exactly the gradient of the energy function. And you can essentially the lens-driven sampling procedure in diffusion models can be basically equivalent casted in the energy-based framework. Roughly just if you just treat the denoising function as a gradient of the energy function, they're both equivalent. So essentially, so in this talk, I'll use both these energy-based models, which were a lot of our earlier works, as well as diffusion models, which are some of our later works. But like you can cast both of them under this energy framework. And it turns out that with this diffusion model, normally you don't have an energy function, you just have this denoising function. But it's pretty easy to also change the diffusion objective so that you actually learn the energy function explicitly. So why energy functions? So I talked about earlier, so in the intro, I talked a bit about this adaptability and research process. Another thing that's really attractive about these models is the idea of compositionality. So if I have this red truck energy, so let's say I have this red truck energy function. If I directly sample from it, I get an image of a red truck. But the benefit is at inference time, I can take a red truck energy function as well as a desert energy function, and I can simply combine both of these. So I can just add the two energy functions together and jointly optimize. And this allows me to get an image of a red truck in the desert. And in practice, when you combine these energy functions, because you don't actually know the scales of these energy functions, you do have to put some care in scaling the magnitudes of the energy functions to prioritize the factor or quality you want. Okay, so what does energy functions buy you? Let's first consider two energy functions. So let's say we have one energy function that has low energy in all points in the blue set and high energy everywhere else. And we have a second energy function that has low energy in all points in the orange set and high energy everywhere else. Now, if I just simply take the addition of the two energy functions, now I get a new energy function that has low energy exactly in the points in the intersection of the two sets. In contrast, if I take the soft min of the two energy functions, I get a new energy function that has low energy exactly at all points in either set 1 or set 2. And finally, if I subtract one energy function from the other one, now I get low energy in exactly points in one set that are not in the other set. So roughly, these energy operations allow you to perform set operations on inputs. And you can nest these set operations if you suitably normalize and threshold the energy functions also. So here's an example of this. So what we did is we trained an energy function for different relations. So we trained it to like generate images of a gray cylinder behind a yellow cube or a gray cylinder below a brown cube. And at test time, we can now generate an image of a gray cylinder behind a yellow cube and not a gray cylinder below a brown cube. Or we can nest these operations a bit more. So we can also generate images of a gray cylinder behind a yellow cube and a gray cylinder below a brown cube, which are these left two images, or a gray cube behind a brown cube and a gray cube out of a blue sphere, which are these two images. So roughly, this gives you a lot of flexibility at test time to generate exactly the sets you want. And more broadly, you can also use these these energy operations to realize different types of probability distribution compositions. So you can use this to represent the product of two distributions by simply adding the energy functions. And you can also use this to realize the mixture of two distributions by doing some type of weighted softmax between the two energy functions. And finally, you can also use these operations to do the inversion of one distribution with respect to the other one. And it turns out, and this paper here actually talks about how to properly do these compositions with diffusion models also. So it turns out that then the normal way where people combine score functions in diffusion models actually ends up being mathematically inaccurate. But you can actually, if you directly interpret the diffusion model as defining a set of energy-based models, then there is a mathematically accurate way of composing the distributions. But it turns out the base diffusion formulation doesn't actually allow you to compose distributions accurately. Okay, so once you have these combinations of distributions, you can then use these operations. Like let's say I want an image of a horse where it's either a sandy beach or a grassy plains where it's not sunny. You can kind of convert this into this probability expression, and then you can get these images of scenes which each of these operations. And the nice thing about doing all of this is that you can train your model on these pretty simple instructions, and now like you can have this model generalize to these much more complex descriptions. So earlier I've talked a lot about so previously I talked a lot about composing these energy functions. The other thing you can also do is you can actually decompose these energy functions. So let's say I have an image here. So if I have an input image here, I can analogously actually infer that energy functions that should be combined together to represent this image. And the idea here is, given this input image, I want to find a set of energy functions that describes this image. And roughly the training objective for this is you just simply train some encoder to infer some set of latents so that the summed energy functions, when they are optimized, reconstructs your original image. So it's a pretty simple objective, just like instead of trying to generate an image, now we're trying to infer the set of energy functions that can be combined together to describe your image. And what we find is that this is able to discover pretty meaningful parts of an image. So here on the top, we have these four objects. And what we find is that each of these individual inferred energy functions corresponds to individual objects in the scene. And in contrast, given this image of a face here, each of these energy functions seems to get these like different parts of the image. So whether it's the face, it's some type of skin tone, some background, or some hair color, roughly each of these energy functions gets you a part of the image. And now by taking the sum of these energy functions, you can now reconstruct the original image here on the right. And the benefit of being able to really infer these components is that it really allows us to generalize and generate new data sets. So here we have two separate data sets that we've trained two separate sets of models on. So in the first data set consists of spheres and cubes. And the second data set consists of the boots and trucks. And essentially, our first model infers, so the first model trained on this first data set basically discovers energy functions for each object. So it discovered these cubes and spheres. And the second energy function discovered these different boots and trucks. And now by combining these two energy functions from dataset 2 with the two energy functions in dataset 1, we can actually generate these scenes are completely novel, where these scenes have both cubes and spheres, as well as boots and trucks. So essentially, by inferring the right independent components, we can now generalize and generate these new scenes that you've never seen before. You can also use this approach to really understand novel scenes. So similar to that previous. So the previous setting, I was showing how you can get these image components that describe the parts of the scene. Instead of getting these image components, you can instead imagine training an energy function condition on the positions of objects. And now when I give you this input image here, you simply want to find the set of positions of objects so that I can reconstruct this image. So instead of trying to infer these latents, and now you're just trying to infer the positions. And essentially, this gives you a way to like understand scenes. So here we have these test images. And roughly, given these test images, we simply just try to infer the coordinates of three composed energy functions so that you can reconstruct this image. And what we find is that this approach of inverting the energy function to find the positions of objects allows us to pretty reliably find the set of 3, 4, and 5 objects, while other approaches have some difficulty doing this. And this is especially interesting when we have all these scenes where now you have 6 or 7 objects. So we've trained these models on only like 3 or 4 objects, but now by inverting these, like finding the parameters of a set of 7 or 8 composed energy functions, we can actually find the positions of all these objects, even if the objects are a lot more than we've seen at training time. And finally, you can also do this on these scenes that are pretty different. So we just trained the model on these images here. But by doing this inversion, we can actually also understand these pretty complex scenes with new textures. And another thing we can do is actually we can also find the number of objects in the image. So what we do is we can try to explain, so given an image, we can try to explain it using 3 energy functions, 4 energy functions, 5 energy functions, and so forth. And we find that if the scene has 4 objects, then explaining it with 4 energy functions gets the lowest error. Similarly, if you have 5 objects, then explaining it with 5 energy functions gets the lowest error, and so forth. Okay, great. So that was a brief introduction on energy functions and compositionality. The next 2 sections will be pretty quick, but I'll just talk a bit about how we can use this energy. So first, I'll just talk a bit about how we can use these energy composition operations to actually do planning. And the big picture is pretty similar to the image setting. So if I'm a decision-making agent and I want to make decisions in the world, roughly I have one energy function that specifies what are valid trajectory dynamics in this environment. And I can have a separate energy function that really specifies the objective functions I want to optimize, whether it's the goal I want to reach, a value function, reward function I want to optimize, or some type of test time constraints. And now roughly what we do in this scenario is we can have one energy function for the entire trajectory. And we can have a separate energy function, which is just a reward function. And now, so if I have one energy function that just models the dynamics of the trajectory, and a second energy function that just specifies different rewards, by directly optimizing the sum of these 2 operations, I can just get a goal-seeking policy. So this is roughly corresponds to planning or reinforcement learning. So by optimizing both of these energy functions, we're essentially just optimizing the reinforcement learning problem. So by a 0-shot combining these models, I can solve a reinforcement learning problem. And what we find is that this type of 0-shot composition, which is this approach here, actually performs as well as many of the existing state-of-the-art offline reinforcement learning benchmarks, illustrating how this is a pretty powerful way to solve these decision-making tasks. And you can also use this type of composition operation to do some type of goal condition planning. So here, let's say you have an energy function for trajectories in the environment. You can just hand construct energy function that's a direct delta that specifies I want to be at a start state S0, and I want to reach a goal state G. And by directly optimizing the sum of these 2 energy functions, now you only get trajectories that have your start state S and your goal state G, while that also satisfy the dynamics of the environment. And this essentially allows you to construct a 0-shot goal-seeking policy through composition. So here we have all these random trajectories in this maze, and then we fix the start state and goal state. And by running this optimization process, we can get these trajectories that can go from start state to goal state. Where here, the environment is pretty, this is a pretty long horizon task. So you have around 512 steps of trajectories, but you can effectively go from your start state to goal state. And we find that this approach, because it requires no training, allows us to do both very good single task planning as well as very good multitask planning. In contrast, like offline reinforcement learning methods require task-specific training because you need to learn their value function per task. And things that require like just use the ground truth model, so something like MPPI, also don't work that well because the horizon of the task is very long. And the final thing you can do is you can take your dynamics energy function, you can combine it with some type of cost function over your trajectory. And this allows you to essentially do test time adaptation. So here we have this unconditional energy function that's able to just stack blocks. And now you can hand construct this energy function that specifies I want the gray block on top of the purple one, the purple on top of the red, and the red on top of the blue. And now by combining these models together, we can now stack the blocks one on top of each other. So this allows you to, and this constraint is just hand designed. So this allows you to really change your behaviors based off whatever constraints functions you specify. And similar to the previous section, you can do all types of learning or like inference or like scene understanding like in the trajectory space also. So one thing you can do is you can use given this type of trajectory energy function and given like a couple demonstrations of a new task you want to learn, you can simply just quickly like fine tune and learn a new cost function for specifying that new task. So here we've trained this model on 4 different tasks, going on a highway, exiting, merging, or going along an intersection. And then now we have this new task where the model needs to actually go around this roundabout. And what we do is by just simply fine-tuning an energy function on a couple of demonstrations to represent the goal of this task, now we have a system that can actually loop around the circle. So this approach allows you to pretty rapidly learn new tasks. Here's another couple examples. So here we've trained this model to push objects around on the table. And now by combining this model together, we can solve a new task of pushing these objects on a book. And then another thing you can do is you can also combine these energy functions at the chunk level. So you don't have to just define these energy functions over your entire trajectory. You can combine them over chunks. So here we have this really large maze. So because it's a huge maze, it's really hard for us to construct a construct a model that just directly generates the energy function over the entire trajectory. And what we can do is we can now essentially infer a set of energy functions where each one just represents a segment of the trajectory. And now by combining them together, we can now form this entire long maze plan. And then the benefit of being able to combine these energy functions over chunks is that it really allows us to be able to combine behaviors combine behaviors together to form really interesting, more complex behaviors. So here we have this data set of trajectories. So in this data set of trajectories, roughly this ant is just like wandering around. So it never really is able to systematically move anywhere. It just kind of wanders in its place. But now if we combine a set of energy functions together and jointly plan, now this model is able to actually go from your start state to the goal state. So it turns out by combining these energy functions over segments, we can actually form these new trajectories that allow us to effectively plan in the world. Yeah, and then you can also use this to combine constraints. So I'm just going to quickly skip over this. But roughly the idea is you can also use these energy functions to specify what if you want like objects in a box. And by just combining these constraints together, you can arrange objects in new flexible ways. You can use them to actually stack blocks together. And you can also use them to solve new manipulation tasks where you can just formulate all these robotics tasks as a set of constraints between objects. Okay, so the final part I'm going to talk about is how you can use these energy functions as a way to do reasoning and a way to solve new tasks that you haven't seen before. So what you can do with these energy functions is that you can roughly use them as a form of reasoning. So you can formulate solving a task is simply optimizing for a solution that minimizes the energy function. So you can just formulate your prediction problem is finding a value x star that minimizes your energy function. And roughly this looks like this. So let's say I want to solve a summation task where I be given 2 inputs x and y. I can roughly formulate finding my final solution is just starting a point somewhere outside, like somewhere here, for instance, and then just running gradient-based optimization until I hit a minima of the energy function. And so energy functions allow you to really have this type of iterative reasoning procedure. And what we find is that this type of iterative reasoning behavior, because you're roughly learning the verifier as opposed to explicitly generating the solution, it allows you to use many steps of optimization as an effective way to improve your test time performance. So by running more steps of computation, we can essentially generalize from like size 10 graphs all the way to these size 30 graphs. While a recurrent neural network, as you try to have it generalized to these larger graphs, the performance gradually gets worse and worse. And yeah, and you can find on a set of benchmarks that like if you use this type of iterative energy reasoning procedure, you actually get better generalization. And the main benefit, again, with these energy functions is that you can actually combine multiple energy functions together in order to solve tasks that are much more complex than the ones you've seen before. And essentially the idea is that we can, if you train energy functions for let's say putting a queen on a set of 8 blocks, now you can combine many instances of this energy function together in order to specify the placements of 8 queens on a chessboard. So this is known as the n queens problem, where you essentially combine energy functions over this row, this row, this row, this column, as well as these diagonals. And by just combining these energy functions across all of these rows and diagonals, we're able to successfully place these n queens on the board, as well as we can solve these tasks like graph coloring or crosswords. So essentially, by combining energy functions together, you can actually use these energy functions as a way to solve these tasks that are much, much more complicated than the individual components you've learned. And we find that this type of composition actually ends up being able to work quite well. So we also have some like proposed methods for optimizing the problem well. But essentially, this allows you to solve a large number of pretty complex reasoning tasks, such as n queens, 3-stat problems, as well as graph coloring problems. And as an example, you're able to solve the n queens problem 97% of the time, even though you only trained a single energy function per particular row. And we compare as another example, we compared this approach for solving stat problems. So here we just combine 91 different, or I believe we have 91 clauses. So we essentially we combine 91 different energy functions over 3-stat clauses, and then we jointly optimize all these energy functions to solve the overall 3-stat problem. And we find that this approach is able to outperform a number of these state-of-the-art neural stat solvers. And the other thing is it actually generalizes much better than these neural stat solvers. So now you can test on like over 218 compositions of energy functions. So overall, I've talked a bit about this idea of energy functions, how you can compose them together, how we can use this composition to solve new planning problems, and finally, how we can combine these models to do reasoning. Thanks everyone for listening. Yeah, and happy to take questions, I guess, probably at the end of the at the end of the next talk.
Thank you very much for this great talk. We will now move on to the flash talk speaker, Sihyun.
Okay, so thank you for having me here. So in this talk, I'll start by introducing our recent work REPA and then how it reshaped the IT training in representation perspectives by extending REPA. So recently, diffusion or flow matching models are showing very amazing success in image or video generation, to name a few, like Sora, Stable Diffusion 3.5, Flux, or Dream Machine, ZagVio, and so on. And like most of these models are now using diffusion transformers, like DITs for short, as their architecture backbone. And mainly due to their scalability and architecture simplicity, which do not contain any complicated components such as like skip connections and so on. However, like training DITs remains like extremely costly. So for instance, even on ImageNet, it requires like more than 1,000 epochs to achieve state-of-the-art FIDs. Which means like we need to use more than a week using like 800 GPUs. Meanwhile, like recent work observed that diffusion models can learn acceptable discriminative representations because inherently like diffusion models is a denoising autoencoder that tries to denoise a noise from a noisy image or noisy inputs. So which means the model do learn some meaningful semantics, and they can be used in like a variety of downstream tasks such as classification or some other levels of dense tasks such as segmentations. However, their representation quality still lags behind that of like recent state-of-the-art self-supervised representations, and we haven't know if this representation indeed similar to that of like representation learned from self-supervised learning schemes such as like Dino version 2 or so on. So in this work, we focus on the opposite a little bit under explore direction, like representation for generation rather than generation for representation. So specifically, we ask like, can good representations improve training efficiency and generation quality of diffusion models? So to explore this question, we begin by like analyzing the representations learned by pre-trained SITX large model, which is the DIT architecture trained with a flow matching objective on ImageNet. And we made several key interesting observations. So first of all, like consistent with prior works, we find that this model does learn acceptable discriminative features indicated by like reasonably high linear probing results. Like you can see the accuracy like at the peak, this is like about 60%. However, this is a way worse than like recent powerful visual encoders such as Dino version 2 or Dino version 3. Second, we also evaluate the CKNNA metric, which measures the alignment between two representations from different encoders. And surprisingly, we observed that like these representations are already partially aligned with like recent state-of-the-art representations, such as Dino version 2. Most like the alignment observed among state-of-the-art SSL models, such as like alignment between Mocha version 3 and Dino version 2. Finally, we analyze how this alignment evolves with increasing the model size and the training budget. So we find that this alignment does improve, but the gains are very, very inefficient and slow. So you can see the curve increases very a little bit, even though we increase the model size from the base configuration to X large configuration, and the slope is very small as well. So it still reaches very low alignment, even though we trained the model with like 7 million iterations. So based on these observations, we hypothesized that like inefficiency in training diffusion transformers lies in like learning good representations inside the model. So specifically, we argue that diffusion models should first focus on learning good representations before like reconstructing the fine pixel level high frequency details, and that denoising object alone may be insufficient to achieve this representation learning. So we show that like, if we can like explicitly guide the representation learning of DITs using external powerful representations learned from another objective, then the training process could be much more efficient and effective. So we introduced a very simple yet effective visualization called REPA that can guide representation learning of diffusion transformers. So simply put, this is like this distillation loss from pre-trained SSL representations into diffusion representations. So we maximize this like similarity between clean image representations obtained from pre-trained visual encoders and noise image representation from diffusion models. So empirically, like we use some cosine similarity as a similarity function and do some patchwise maximizations between patchwise features from pre-trained visual encoders and diffusion transformers. And we found the model trained with REPA shows very different behavior from the vanilla model trained with only the denoising objective. So first, we observed that the model trained the REPA using Dino version 2 shows like reduced semantic gap compared with the vanilla model, shown by improved linear probing accuracy and image depth. So this is quite expected because we explicitly distill the representation to the diffusion transformer. And we also find since we explicitly made alignment with Dino version 2, we also found the alignment score better by KNNA also improves. And the last and the most interesting part is the third figure. So we also find that this leads to much more improved generation performance compared with the model, like banana model counterpart trained with the same iteration, as shown by like much better FID at the same training iteration. Yeah, so I think qualitatively you can show the difference much better. So we also show that like RepI enables much better visual scaling, and the model produces like dramatically better generation at the same training iteration. So for instance, you can see the model trained with RepI captures the overall shade of the shark much better than the banana model. And we also showed this visualization is very scalable in terms of various perspectives. First, we find that RepI is scalable to the quality of target representations. So we sweep the target representations from MAE to Dynaversion 2. And we show that like improving the target representations not only improves the like linear proving accuracy, but also improves like generation performance measured with FID. And we also find RepI is scalable with respect to the model size too. So if we compare the like relative convergence among different model configurations, so we find that larger model trained with RepI reaches the same FID level of the same like banana model counterpart much faster. Yeah, this is also like consistent, so similar finding to the previous figure. So we find like larger model shows deeper performance gain with RepI, indicating that larger models we can like achieve better, much more improved discriminated power as well as better generation performance with RepI. So based on these results, we also conduct like system level analysis on ImageNet by using Dynaversion 2 as a target representation and fix the alignment depths. And like without classifier-free guidance, we find that like RepI can accelerate diffusion transformer training over like 17 times, and with classifier-free guidance, it can achieve over like 7 times more speed up. Furthermore, with longer training and the guidance interval techniques, we also find we also show RepI achieves a state-of-the-art FID score of 1.42. We also conduct experiments on higher resolution dataset by using ImageNet 512 by 512. And similar to previous results, we also show that RepI can achieve very incredible improvements in higher resolution dataset setup. And finally, we like evaluate RepI on text to image generation using the like MS Coco dataset. So we want to try a larger dataset, but we couldn't do that due to the lack of resources. But like at least on MS Coco dataset, as shown in the table and the figure, you can see RepI greatly improves the text to image generation quality compared with the banana diffusion transformer model. And like not only improving the image quality, but it also does improve image text alignment. For instance, the model trained with RepI in the like this zebra figure, you can see RepI not only generates more realistic zebra, but also like generates the pond and place the zebra at the edge of the pond correctly, while the banana model even fails to generate the pond in the generated images. After RepI, I think there are a lot of works have explored improving training schemes of DIT by adopting like representational viewpoints. So first of all, I think there are some several like follow-up works that have to try analyze and improve RepI and achieve even faster convergence than the vanilla RepI. So for instance, there exists like RepI-E in the figure on the left. So you can see, so this work basically tried to do end-to-end training by fine-tuning VAE encoder as well using RepILOs. And the paper argues it even achieves more training boost than compare with the vanilla model or vanilla RepI model. And the figure on the right, it also shows if we add like more complex representations as a generation target and alignment. So basically they add a like CSS token from pre-trained visual encoder as generation target, and they show it can even more it can achieve even more like generation if it like training efficiency, and the performance becomes much better than vanilla REPA. So yeah, and the another line of work have considered like regularizing and use the latent space to be perceptually aligned rather than like injecting pre-trained representation inside the model. So I think there are two representative works. The first one is VAVAE, as shown in the left. So basically, they use alignment loss when training VAE before training diffusion model, so that VAE latent space to be perceptually aligned with the target representations. Another work is very recent work called RAE, which uses the like frozen pre-trained visual encoder directly as input representation to the diffusion transformer. So they directly model the data distribution in such like pre-trained representations, and then train an additional decoder that try to reconstruct image from the target representation, such as frozen Dino version 2. And it also shows very promising and strong results compared with the conventional diffusion transformers that try to model the distribution in the VAE latent space. Yeah, so in summary, we present a very simple yet effective like regularization called REPA, which can significantly improve diffusion transformer training. So this regularization is based on our hypothesis and observations that like learning good representations might be a key for diffusion transformer training. So we demonstrated that REPA has very great scalability in terms of like target representations, model size, resolution, and like the complexity of target tasks such as text image generation. And like, yeah, we also, so after REPA, I think people have now focused on how to exploiting good visual representation for generative model training. But because like before REPA, people have thought like this self-supervised like representations are not helpful and something like independent to generative model, especially for diffusion model training. So I hope this representation for generation scheme would like be more explored and can eventually build some unified model, or can be extended to other complex data modalities such as videos and more like 3D scenes and so on. Yeah, so this is end of my talk, and thanks for listening. Yeah, please feel free to ask any questions. Thank you.
Thank you both for the great talk. So I will now alternate the question. I will read them from the chat. So I will start first with a question from Berker Demirel. So this is for Yilun. So the question is, not all factors like binary, yes, no. Question, why shouldn't we learn how red the object is rather than if the object is red or not?
Yeah, so with the energy functions, you do actually maximize the likelihood of the data. So the energy function actually is not necessarily binary. So it can actually be continuous. So you can instead represent the extent to which something is red. What happens is as you make these things more and more graded, continuously graded, which I think also might reflect another one of your questions, is that when these values are kind of continuous valued, there's kind of a different now like you get these things where like maybe I want something to be red and I want something to be car, but each of these are continuous values. So what exactly is a red car? Like they might have non like overlapping minima. So now you have some issue where you need to choose the right scalar magnitude to combine them.
Thank you. I hope that answers your question, Berker. Yeah, it seems like it does. Now a question for Sihyun. How, from Edric Castelhau, how degraded can the representation be before they stop providing improvements to the diffusion model? I think you're muted.
Oh, yes. So if I understand correctly, can derail it. Yeah, so I think there are some works that try to do alignment at the beginning of the training and then slightly like reduce the amount of alignment and allow the model to more focus on reconstruction the details by more focusing on the noising task. Yeah, I heard that shows a further improvement. Yeah, if I understand the question correctly. Yeah.
Thank you. And now another question for Yilun from, oh, sorry, one sec. Lilius 1999. So the question is, first of all, he says many thanks for the great talk. He asks, or she has, sorry, have you read the new equilibrium matching paper? If so, do you see it performing comparably well in composition with energy-based models, being kind of a EBM model?
Yeah. So actually another undergrad who worked with me wrote the equilibrium matching paper. So we have been exploring it. So we have recently we have been trying it with different types of composition. Yeah, it seems to work pretty well. So we've been trying some types of planning with the equilibrium matching model, but it seems like things hold pretty analogously.
Thanks. Now we will have a question from Berker, but this time for Sihyun. So we pick the question two. Since the latent diffusion run around VAEs, representation alignment should also be faithful for the VAE decoder. Isn't the VAE encoder itself the best model to align?
So yeah, I think that's a point that people try to focus now on. So yeah, so several works such as BAV try to like try to explicitly regularize encoder part, encoder part by aligning with external representations. And I think like nowadays people even show encoder itself can become pre-trained video encoders, not just like compressing the latent channel for better modeling. So yeah, I think that's a good point and exciting future direction.
Thank you. We also have a question for Yilun from Edric. How does the model react to the addition of an unknown object with an unknown energy function during deployment?
Yeah, so one thing to note is most of the energy functions we compose together, they are trained on separate data sets. So in a sense, we are kind of combining energy functions of new objects. So I've kind of in the paper, in the talk, I mostly showed examples where this is successful. But there are definitely settings where, like, if you have an unknown energy function, especially if it conflicts with an existing energy function, then you'll generate these images that are kind of like adversarial minima, where it's kind of like the images will have some aspect of factor one and some aspect of factor two. So depending on how like disentangled or like conflicting this new object is, things can break. But most of the examples I showed in the talk were compositions of unknown energy functions.
Yeah, I have personally also a follow-up question to that maybe. I'm not really in this field, I work more in deep learning theory, so maybe this is naive, but what are the limitations and places where it breaks easily in these types of method? Because it seems very powerful, and for me it's hard to know where and what are like the technical limitation or general limitation of energy-based models.
Yeah, well, so one thing is, so traditionally they've been pretty hard to train. So the contrastive divergence objective, or I talked about, was pretty challenging to train. With some of these diffusion or equilibrium matching things, these are easier to train. So, but still, like they tend to be a little hard to train. The second one is this optimization problem. So now you're trying to optimize your energy function. And the thing is you combine more and more of these energy functions together, you get these more and more complex landscapes. So the optimization problem gets increasingly harder. And the other thing is, especially when these values are continuous valued, now what is the right weight to apply to these is also like you have this hyperparameter problem where you have these constraints, they're kind of all soft constraints. So what is the right trade-off between the soft constraints to get your desired answer? So I think a lot of so both optimizing the composition is a little hard, and also finding the right weights for the composition can be a little challenging.
Okay, thank you. And maybe before I talk about the next appointment, a last question to Sihyun. So this is the first question from Berker. Since REPA aligns the noisy image when
Oh, I think maybe the audio is cut off. Yeah.
Yeah, I think I can just go read the question and answer.
Yeah.
Yeah.
Sorry. Can you hear us?
Yeah. Yes. I will just read the question.
Recording in progress.
Sorry, my connection failed for a second. Did you answer the question? Did you hear my question or?
Yeah, I will just read the question and answer it. Yeah. So even though T is large, it is alignment still matters because it still learns the so for instance, for image generation, it still learns the expectations of classified representations when T is large. So it still guides the trajectories to be more discriminative at the large time step. So it will be effective to overall sampling process. So we also tried aligning at the certain time step intervals, but usually aligning throughout the all time step will is usually very beneficial compared with just constraining the alignment to certain times of interval.
And we will have Dinglin who will ask a question before I present the next speakers.
I should ask myself. Thanks a lot for the amazing talk. Yeah, I'm the poor one who got the question skipped because I'm the co-organizer. But I have a very interesting in your talk and have a question for you. So basically, I remember one of the example you're showing, about the different objects, and basically you have one energy function of, say, brown objects on the top of the yellow one, and another energy function is for example, the red ones on the right-hand side of the blue one. And you basically add both of energy function, you get this kind of compositional generalization. From my point of view, please correct me if I'm wrong, it sounds like the composition is encoded on the relation level. Basically you have this object A, object B, and their relation pairs per se. And based on this level, you try to generalize across different scenarios. I mean, my naive interpretation is you might need this for the independence assumption you mentioned at the very beginning. I am very interested in do you see any possible extensions of your energy-based model framework for, on the object level, object level decomposition? Basically, you have energy function encoded for individual objects, but on the top of that, you also model the relations between these objects explicitly.
Yeah, I think that's a great question. I think you can kind of factor the distribution you want to model. So right now, you're right. So we're doing object one, object two relation. But you could imagine you maybe have a model for object one and a model for object two, and then you have a model P of relation given object one comma object two. So if you factorize it in that way, So you can imagine that you have energy function for each object, and then maybe you take the features of the energy function, and then you learn a relation energy function on top of that. So if you have a hierarchical model in that way, now you can factorize at object level.
I see. That sounds pretty good. But like it will also come with the challenge you mentioned before that the more composition you have, basically there are some technical challenges you have in training.
Yeah, it becomes harder to optimize. I think if you train all the models together, I think the most we managed to compose is in these reasoning settings. So we're able to compose around 200 models there. But we did have to come up with new optimization algorithms to do that, and we also trained the models in combination. So you would have to need to do some tricks if you want to decompose it into mini parts.
I see. Thank you so much. Thank you.
Thank you both, and thank you everyone who attended this talk today. I wanted to present, one second, I'm trying to move my slides. The next speakers for the next appointment. Oops, sorry. So we will have, sorry, one second. We will have Menaski Kozla from UC San Diego as a keynote speaker, and for the flash talk, Raj Magnesh. This will be on the December 10th at 4 CET as well again. Thank you everyone for attending, and thank you to the speakers for the great talk. And yeah, have a good rest of your day.